Welcome to a Xilinx Quick Take video. My name is Jason Lawley, Technical Marketing Manager with Xilinx. In the video today, we're going to look at some debug capabilities available to help get a PCI Express link up and running. The PCI Express protocol makes it so that every time two PCI Express devices are connected, they negotiate how many lanes are enabled, called the link width, as well as how fast the link operates, called the link speed. Xilinx devices operate from Gen 1, which is 2.5 gigatransfers per second, with a link width of by 1, all the way up to Gen 3, which is 8 gigatransfers per second, with an industry-leading width of by 16. Because link negotiation is the first thing that has to happen before we can move actual data across the link, and the fact that there are often chips from multiple vendors involved, having a simple and easy way to assess what is happening at the link level can save days or even weeks of debug time. Starting with our UltraScale Plus family of devices, Xilinx has added multiple link debug features to our PCI Express IP to make the link debugging easier and faster than ever before. We'll start by looking at our JTAG Debugger, which lets you visually see different link training state machines, including the LTSSM state machine. Next, we'll look at the in-system iScan, which lets you look at eye diagrams while PCI Express traffic is running through the transceiver. Finally, we'll explore two Gen 3 Descrambler blocks, letting us look at unscrambled data passing between the PCIe block and the transceivers in both simulation as well as hardware. We'll look at all three of these debug features running on our VCU 118 board, allowing us to run our PCIe link at up to Gen 3 by 16. Let's go ahead and get started. Now we already have our Vivado project open, targeting the VCU 118 board. We'll go ahead and open the IP catalog and search for the PCI Express IP that we want to open. In this case, we're going to do the DMA bridge subsystem for PCI Express. Now once that opens, we'll have our GUI to set up different options. We'll select the location for the PCIe reset and select a link width of by 16 for this particular board on the board tab. We'll also change our mode to advanced so we can see the tabs that we need to have. And we will need to select the link speed to be 8 gigatransfers per second or Gen 3. Now here's the three debug options that we're going to look at. Note that when Gen 3 is enabled, that's the only time that you'll see the Descrambler mode to be picked. Okay, we'll go ahead and get our XCI file. We'll go ahead and right click on it and select that we want to open the IP example design. We'll select the location of where we want that example design to be. And once we do that, when we say OK, we'll go ahead and Vivado will generate a new Vivado project with the PCI Express IP as we've configured it with our example design. Now when we open the design up, you'll see that there are two free running clocks. These free running clocks are needed for us to implement our iScan and will only show up if iScan has been enabled. Let's go ahead and add a constraints file, and now what we're going to do is add the Descrambler blocks to our debug setup so that we'll be able to capture those in chip scope. So we'll create our new debug XDC file. We'll set it so that it's not in synthesis, as we don't need it there, and we'll set it as the target. Once we've done that, we can go ahead and run our synthesis. Once that synthesis design completes, we'll go ahead and open it up. And once it's open, we'll go ahead and do setup debug. Now there's going to be some extra signals in here that we don't need, and you'll see these in the debug wrapper. That debug wrapper is for our JTAG debug mode, which lets us read those state machines. We could look at that and trigger on that if we wanted to. We don't need it in our case, so we'll go ahead and delete that and have only the descrambled signals. Now here we can add some different ILA core settings. We're going to leave those as the default, and we'll go ahead and say finish. That will go ahead and set up our debug. And once our debug is completed, we'll go ahead and close the synthesized design. When it asks us to save, we'll say yes. That will store all of our constraints to our debug XDC file. So now if we go and look at that debug XDC, we should see that all those constraints are there to add our descrambler logic to our chip scope module. All right, now we'll go ahead and run implementation on this design. And once it's complete, we can go ahead and open it up real fast. And we can zoom in. We'll see our PCIe block there is the big red block. And then our transceivers are up the right-hand side. We see that timing has been met. We can go ahead and close this, and now we're ready to generate a configuration bitstream. So we'll go ahead and generate that bitstream, and we'll speed that up and let it run. Once that bitstream is completed, we'll open the hardware manager. We already have a VCU 118 device connected to our design, to our PC. We'll go ahead and auto connect to it, and now we can go ahead and program it with our bitstream. Now in this case, we have that VCU 118 plugged into a PCIe Express slot in a server. And once we have turned that server on, we will see that we're getting packets that are coming across, and we're able to capture different things. All right, so the first thing we want to do is we need to, for our JTAG debugger, we need to go into this meminit location, and we need to source a tickle file. That tickle file is going to go and read the information from our JTAG debugger and store it in a bunch of text files. We have those text files stored. Now we need to jump outside, and we actually have to have Tickle, standalone Tickle installed for this. And so we go into that same meminit files directory, and we can run our reset state machine. Now here we see that all of the reset states should have been hit, which is a good sign. That's what we want to see. If for some reason we got stuck in one of these states, you would not see them all be green, and that would give you a hint that there's some kind of issue with reset. Next, we'll look at TX detect RX. In this case, we're plugged into a byte 16 slot, so we see only 8 of those locations are available. And here we see our LTSSM state machine. So the orange is we're in the L0 state, which is where we want to be. The green tells us where we have been, as well as how many times we've transitioned on each of those paths. So that really quickly gives us a good idea of what's going on with our link and if we've link trained. Now let's take a look at the in-system iScan. Here we're going to go ahead and add a scan, and in this case we are going to select lane 16, or lane 15 in this case, but the 16th lane, 0 to 15, and we go ahead and select OK, and that's go ahead and create a scan, and oh, it's all red. Well, now if you remember, that makes sense. We plugged into a by 8 slot. And so the 16th lane is not receiving any data. So let's go ahead and add lane 0 and see what we get. And we do that, and now we do get an eye that we can discern and see in the middle. And we don't have red there, so that's good. Now we can do things where we can make that iScan more precise, and there's ways to do that, and you can go look at some iScan quick take videos that show you how to do that. Last thing we want to show you is these descramblers. So we're looking at both the receive and the transmit, and we'll go ahead and do a trigger now. In a lot of cases, you'll want to set your trigger to look for something specific. But here you can see that we have a bunch of our pipe interface signals that are going on, and it's easy for us to go and we can go in and look at those. In this case, we have a bunch of idle symbols, but this lets us, if we're looking for something specific, we can set a trigger and then make sure that either we're receiving data from the transceivers correctly or sending it out correctly. So that concludes this quick take video. We hope that you'll be able to get to link up with your PCI Express designs. Thank you very much.